Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Walther Hermann Nernst, a figure of considerable stature in the annals of physical chemistry, presented his Heat theorem in 1906, a contribution that reshaped the understanding of chemical thermodynamics and laid a cornerstone for the development of quantum mechanics. To appreciate the profound significance of this theorem, it is essential to examine the intellectual landscape from which it emerged, the core tenets of the theorem itself, its immediate and subsequent impacts, and the critical reception it received. Prior to Nernst's intervention, classical thermodynamics, while remarkably successful in describing macroscopic phenomena, encountered difficulties when applied to chemical reactions, particularly at low temperatures. The Gibbs-Helmholtz equation, a central tenet of classical thermodynamics, relates the change in Gibbs free energy, delta G, and the change in enthalpy, delta H, of a reaction to the temperature, T, and the change in entropy, delta S, by the relationship that the change in Gibbs free energy equals the change in enthalpy minus temperature times the change in entropy. This equation proves invaluable for determining the spontaneity of a chemical reaction at a given temperature. However, it offers limited insight into the absolute values of thermodynamic quantities, especially as temperatures approach absolute zero. Determining equilibrium constants at varying temperatures required careful calorimetric measurements of heat capacities over a wide temperature range. This proved experimentally challenging and practically limited predictions at extremely low temperatures. Furthermore, classical thermodynamics provided no inherent mechanism for calculating absolute entropies. Only entropy changes could be determined through integrating heat capacity measurements. This limitation hampered the precise determination of chemical affinities, which are essential for predicting the equilibrium composition of reaction mixtures. In essence, while the Gibbs-Helmholtz equation provided a framework for understanding the temperature dependence of chemical equilibria, it did so within constraints. This framework relied on empirical measurements and inferences drawn from those measurements, without providing a fundamental anchor at absolute zero. Nernst's heat theorem, initially formulated as a purely empirical observation, addressed this deficiency. It essentially stated that, at absolute zero, the change in entropy, delta S, for any condensed phase chemical reaction approaches zero. Mathematically, this can be written as the limit as temperature approaches zero of delta S equals zero. This deceptively simple statement held far-reaching consequences. It implied that the Gibbs free energy change, delta G, and the enthalpy change, delta H, approach each other asymptotically as the temperature approaches absolute zero. In other words, at sufficiently low temperatures, the driving force for a chemical reaction becomes purely energetic, with entropic contributions vanishing. Nernst's initial formulation applied strictly to condensed phases, meaning solids and liquids. He posited this limitation based on the understanding that gases, even at extremely low temperatures, might exhibit more complex behavior. Extending the theorem to gases required a deeper understanding of their quantum mechanical nature, which was yet to be fully developed at the time. Furthermore, Nernst emphasized that the theorem applied to reversible processes. Irreversible processes, inherently involving entropy generation, would not necessarily adhere to this limit. The immediate impact of Nernst's heat theorem reverberated across physical chemistry. The theorem provided a crucial constraint on the behavior of chemical systems at low temperatures, thereby enabling more accurate calculations of chemical equilibria. By extrapolation from experimental data at higher temperatures, thermodynamic properties could be accurately predicted down to absolute zero. This advancement proved particularly useful in various industrial processes involving low-temperature reactions. Perhaps more significantly, Nernst's theorem offered a pathway to determining absolute entropies by integrating heat capacity data from a temperature near absolute zero upward and invoking the heat theorem to set the entropy at absolute zero. Absolute entropy values for various substances could be established. This provided a foundation for calculating standard entropies and Gibbs free energies, drastically improving the accuracy of thermodynamic predictions. This meant that it became theoretically possible to calculate the absolute entropy of any element or compound by measuring the thermal energy required to bring it from absolute zero to a specified temperature, assuming that one could measure down to near absolute zero. The impact also extended beyond purely chemical applications. The heat theorem provided a crucial link between thermodynamics and statistical mechanics. Statistical mechanics, pioneered by Ludwig Boltzmann and Josiah Willard Gibbs, seeks to explain macroscopic thermodynamic properties in terms of the statistical behavior of microscopic particles. Nernst's theorem provided crucial experimental validation for certain statistical mechanical predictions regarding the behavior of systems at low temperatures. It bolstered the confidence in statistical mechanical approach. The heat theorem also played a pivotal role in the development of quantum mechanics. While Nernst initially framed his theorem within the context of classical thermodynamics, its implications suggested the need for a fundamentally new understanding of energy quantization. The observation that entropy changes vanish at absolute zero implied that the number of accessible microstates available to the system becomes severely restricted at low temperatures. This observation implicitly hinted at the discrete nature of energy levels, a central concept in quantum theory. In fact, Nernst himself became a strong advocate for quantum mechanics, recognizing its potential to provide a deeper theoretical foundation for his theorem. One particularly striking example highlighting the interplay between Nernst's heat theorem and the nascent field of quantum mechanics involves the behavior of specific heats at low temperatures. Classical statistical mechanics, based on the equipartition theorem, predicted that the molar specific heat of a solid should approach a constant value, 3 times the ideal gas constant, at all temperatures. However, experiments revealed that the specific heats of many solids decreased significantly as the temperature decreased, deviating dramatically from the classical prediction. Nernst's heat theorem provided a crucial clue. As the temperature dropped, the entropy change approached zero, meaning that the atoms or molecules could occupy fewer and fewer energy states. This led to the realization that energy was not infinitely divisible, as assumed in classical physics, but rather quantized into discrete packets. This insight ultimately contributed to Albert Einstein's groundbreaking work on the quantum theory of solids, which provided a successful explanation for the observed decrease in specific heats at low temperatures. Einstein's model, while simplistic, captured the essential physics by proposing that the vibrational energy of atoms in a solid is quantized. This model provided a significant leap toward explaining experimental observations that baffled classical physics. The reception of Nernst's heat theorem proved multifaceted. Initially, some prominent thermodynamicists greeted it with skepticism. The theorem, being empirical in origin, lacked a rigorous theoretical justification. Some argued that it appeared as an ad hoc hypothesis designed to reconcile classical thermodynamics with experimental observations. Wilhelm Ostwald, a staunch proponent of classical thermodynamics, expressed reservations about the theorem, questioning its generality and its implications for the broader framework of thermodynamics. However, as experimental evidence accumulated in support of the theorem, and as quantum mechanics began to emerge, the initial skepticism gradually waned. Max Planck, a leading figure in the development of quantum theory, recognized the profound importance of Nernst's work. He praised its ability to bridge thermodynamics and quantum mechanics. Arnold Sommerfeld, another influential physicist, highlighted the theorem's role in guiding the development of quantum statistics. Moreover, the persistent critiques prompted further refinements and extensions of the heat theorem. Max Planck, for instance, attempted to provide a more rigorous theoretical basis for the theorem using quantum statistical mechanics. He showed that the theorem could be derived from the assumption that the entropy of a system approaches a finite value, typically zero, as the temperature approaches absolute zero. While Planck's initial derivation contained subtleties, it represented a significant step toward grounding the theorem in a more fundamental theoretical framework. Later work by researchers such as Fowler and Guggenheim further refined the understanding of Nernst's heat theorem. They clarified the conditions under which the theorem applies, and they extended its applicability to a wider range of systems, including gases under certain conditions. They emphasized the importance of quantum mechanical effects in understanding the behavior of matter at low temperatures. The influence of Nernst's heat theorem extends to numerous subsequent scientific developments. It helped develop the third law of thermodynamics, which formally states that the entropy of a perfect crystal at absolute zero is exactly zero. While Nernst's heat theorem was formulated earlier, the third law is considered a more general and precise statement. The third law has profound implications for understanding the direction of spontaneous processes and calculating absolute entropies. Furthermore, the Nernst heat theorem influenced the development of cryogenic technologies. The quest to achieve extremely low temperatures, driven in part by the desire to test and validate Nernst's theorem, led to innovative cooling techniques such as adiabatic demagnetization and dilution refrigeration. These technologies, in turn, have enabled groundbreaking research in condensed matter physics, superconductivity, and other fields. In conclusion, Walther Hermann Nernst's heat theorem, presented in 1906, represents a pivotal contribution to chemical thermodynamics and quantum mechanics. Emerging from the limitations of classical thermodynamics at low temperatures, the theorem posited that entropy changes vanish at absolute zero for condensed phases. This seemingly simple statement unlocked a cascade of implications, providing a means to calculate absolute entropies, validating statistical mechanical predictions, suggesting the quantization of energy, and ultimately informing the third law of thermodynamics. While initially met with some skepticism, the heat theorem gained recognition as experimental evidence accumulated and quantum mechanics flourished. It shaped the direction of thermodynamics, statistical mechanics, and quantum mechanics, fostering innovative cryogenic technologies that continue enabling groundbreaking discoveries in diverse fields of scientific research. The heat theorem stands as a testament to the power of empirical observation, combined with theoretical insight, to drive scientific progress.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.